Welcome to video 26 on the TTB course. This video is from part 5 of the TTB course. In part 5 we introduce a set of TT platforms that are intended to speed up the development of safe and reliable time-triggered embedded systems. We then illustrate how these platforms can be applied in a range of case studies. In this video, we consider in outline the design of a controller for a gas turbine engine on a passenger aircraft. This example is intended to illustrate one way in which the techniques presented on this course can be extended to meet the requirements of SO4 and equivalent systems. The material in this video is based on the ERES2 book, chapter 26. If you haven't yet read the book chapter, I suggest you read the chapter first before viewing the video. Everything will make much more sense if you do things that way around. Throughout this course, our focus has been on designs that need to meet the requirements up to SIL 3 in IEC 61508 or ASO D in ISO 26262 and equivalent levels in other standards. There's a level above this. SIL 4 or Design Assurance Level A systems, DAL-A, according to DO 178C, these requirements are the most challenging that designers have to meet when developing safety-critical systems. We'll consider some of the challenges involved in creating DAL-A design in this video. Our focus will be on the development of a controller for a gas turbine engine for use in a passenger aircraft. I should make it clear that SIL 4 requirements don't at present apply in all sectors. For those used to working in the automotive sector, for example, SIL 4 is the equivalent of ASIL E. In my view, we may need to consider an ASIL E classification for autonomous road vehicles in due course, but such a classification does not yet exist. The figure below shows a Rolls-Royce Trent 500 turbofan engine. This is used, for example, in Airbus A340 aircraft. The Trent 500 can generate up to 60,000 pounds of thrust. Control of the thrust level is provided by means of what is called a FADEC, a Full Authority Digital Engine Control Unit. You can see the FADEC unit highlighted on this slide. When you're working in DO 178C, we have 5 levels to consider. These begin at level E, which are effectively SIL 0 designs. So in level E, failure of the system has no impact on safety, aircraft operation or crew workload. At the other end of the spectrum we have level A. These are described as catastrophic failures in DO 178C. In this case, failure would prevent continued safe flight and landing. It's worth noting level B on this scale as well. This is hazardous severe major. This is the equivalent of an ASO D or a SIL 3 design in other sectors. As far as DO 178C is concerned, failure has a large negative impact on safety or performance, or reduces the ability of the crew to operate the aircraft due to physical distress or a higher workload, or causes a small number of serious or fatal injuries among the occupants of the aircraft. So even at level B, we're assuming that failure of the system may lead to fatal injuries. Level A is one step above that. In my view, level A might be considered equivalent to the failure of an autonomous vehicle system on a large and busy motorway, where failure of that system could potentially lead to the deaths of large numbers of people if a multiple pileup is caused by failure of the autonomous vehicle system. Again, these are not considerations in current versions of the related international safety standards. So our DAL-A platform is likely to consist of a duplicator HE framework. What this means is to create the hardware platform upon which we're going to run our tasks to control our gas turbine aero engine, we would probably use two different microcontrollers. Each of these would be SIL3 microcontrollers with a safety manual, but we would deliberately choose different microcontrollers, probably from different manufacturers, potentially even with a different core, to provide a basis for our application. This is likely to be required by certifying authorities when creating such a design. We would probably also have some form of secondary control unit to take over if both of these microcontrollers failed. So we'd have two diverse microcontrollers running appropriate diverse software, and we'd probably have a secondary control unit to take over if both of these microcontrollers failed during the flight. As we discussed previously, this is consistent with our general view that as we increase the safety integrity level of the system, we're likely to have to increase the level of diversity in the design. What about the required task set? The BATE 1998 document that you'll find listed in the ERES2 book lists a set of tasks that could be employed in our FADEC. This task set is based on that used in the Rolls-Royce BR715 engine controller. There are 71 tasks in the set. So we could use that as a starting point for creating the software for this type of design. So this introduces another challenge that we have not yet considered on this course, which is how we would configure such a large task set. So our FADEC design might include 70 to 100 tasks. How do we configure such a large task set? Let's go back and consider our modeling of periodic tasks. So we've met this representation before. Suppose we've got a system of n periodic tasks. Each task can be represented by a tuple, a set of parameters. So we've used the same set previously, where P is the task period, W is the worst case execution time of the task, D is the task's relative deadline, the time measured from the moment that the task is scheduled to start, by which the execution of the current invocation of the task must be completed, and O is the task offset time, the time at which the first invocation of the task occurs. So within this course, we've been concerned about task offsets that are measured in ticks. So a task with an offset of 0 runs for the first time in tick interval 0. A task with an offset of 25 runs for the first time in tick interval 25. So we've seen each task can be represented by a tuple. Some of the parameters in this tuple are fixed. Typically the period is essentially fixed, the worst case execution time is essentially fixed, and the deadline is essentially fixed because the deadline will be determined by our jitter requirements. The only parameter we have left here is the task offset. So if we're going to adjust our task behavior, we often have to consider the task offset as the main parameter that we have control of. Suppose we have a 3-task system. The tasks may be described by the following parameters, all in milliseconds. So we have task A has a period of 20 milliseconds, a worst case execution time of 7 milliseconds, a deadline of 20 milliseconds, and an offset of 0. So what we're saying here is that the deadline is equal to the period. So we're not saying these tasks have any significant jitter requirements. We're just saying that each task must complete before it's scheduled to run again. We're giving each task an offset of 0, and we've got a worst case execution time that's significantly less than the period. So we can calculate, using the techniques that we've discussed previously on this course, we can calculate an appropriate tick interval, could be 10 milliseconds. So we could add these tasks to a schedule using the kind of techniques we've used before in this form. So we can add the tasks to the schedule in this way. So the tasks that have a 20 millisecond period will be added with 2 ticks because our tick interval is 10 milliseconds. So if we consider that task set again, we've got task A, task B and task C with the period and worst case execution time values that we've looked at, and we can look at the average CPU load, or the CPU utilization comes in at 72.5%, excluding any scheduler overheads. So we think it's likely that we would be able to schedule this task set. So in this case, we have a synchronous task set. We've decided that our tick interval will be 10 milliseconds. In the first tick, all of the tasks will run. It's a synchronous task set. So the total execution time of all the tasks that we release in tick 0, tick 4, tick 8, etc. will be 16 milliseconds. And we have a 10 millisecond tick. So we're going to overrun our tick interval periodically during the task execution sequence. Let's look at that situation in slightly more detail. So we've got task A, task B, task C. We have 0 offset, so we have a synchronous task set. We've got the worst case execution time of task A is 7 milliseconds, worst case execution time of task B is 7 milliseconds, and the worst case execution time of task C is 2 milliseconds. So in tick 0, we release all of the tasks, so we have a total execution time of 7 plus 7 plus 2 equals 16 milliseconds in tick 0. And every time during this task set, when all of the tasks are released, we're going to have a total execution time of 16 milliseconds. Our tick interval is 10 milliseconds, so we're going to significantly overrun our tick every time we release all 3 of these tasks. What that means is, at best, that task C, in this case, for example, which follows in the next tick interval, will have a very high level of jitter. Now we worked out the average CPU load to be 72.5%, so we know that we can schedule this task set, but we may be concerned about the level of jitter in task C, and we may not want to run our task set in this way. What can we do? This shows a revised version of the task set. So now what we're doing is we are changing the offset of task B. So we're adding a 10 millisecond or 1 tick offset to task B. So what happens now is that in this task set, we'd never exceed the tick interval. So now we've spread out the task executions more evenly over the tick list, so that in tick 0 now, because of the offset value, in tick 0, task A and task C run. In tick 1, task B and task C run. In tick 2, task A and task C run again. In tick 3, task C runs. And we head on from there. So by adjusting the offset, we've leveled out the total maximum CPU load, and now we don't exceed more than 90% of the available tick interval in any set of task releases in this schedule. There are various other things we can do by changing the offsets. By changing the offsets, we can also control the execution sequence of the tasks. And that may also be something that we need to consider to ensure, for example, that task A always runs before task B, etc. So this slide shows how we could add our revised set of tasks to a schedule using the scheduler add task function in the format that should be familiar to you by now. So we're initializing our scheduler with 10 millisecond ticks. So our offset of 10 milliseconds becomes 1 tick. So we are having an offset of 0 for task A, an offset of 1 for task B, and an offset of 0 for task C in this task set. So if we've got a large task set, how do we determine the task offsets? If we've got a small task set like the one we looked at in the previous toy example, we can work it through by hand and we can easily see what we would need to do to make sure that the sum of the execution time of the tasks did not, for example, exceed the tick interval. What about a larger task set? So in simple examples, we can determine the offsets by hand. In realistic systems, we may have 50 to 100 tasks. We're likely to have to reschedule the task set as the project evolves. If we're going to do this by hand, we can do it, but it's going to be a tedious process. So what we really want to be able to do is to determine the schedule parameters automatically and to be able to report the full schedule, in part to support system verification activities. So if we go back to our engine control example, we reckon we'd have about 70 plus tasks to work with. As we work through that kind of project, we want a mechanism, automatic tool set, tool support that would help us to schedule this task set. Fortunately, we can do this in a very straightforward way. So this is an example of a simple TTC scheduler. We've met this many times. So in this case, in this particular version, once the delay value for the schedule gets to 0, we release the task. And that works quite happily for this version of the scheduler. This is a dry scheduler. It doesn't release any tasks, but this time it's performing a schedulability test. It's part of a schedulability test. So in this case, what the scheduler is doing is it's simply summing up the execution time of the tasks that would be released in a tick, making use of worst case execution time information about that task. So this is the dry scheduler, as we discuss in the appendices to the ERES2 book. It's a dry scheduler, it doesn't release any tasks, but it allows us to perform some schedulability tests. So if we want to perform a schedulability test using a dry scheduler, then this is a technique we can follow. We can arrange the tasks in order of priority, with the highest priority first. We add one task at a time to the schedule, initially with offset 0. We check the sum of the execution times of all tasks in each tick, and we can easily set, say, 70% of the tick as a limit. We simulate the task set over the period that's given by the length of the hyperperiod plus the maximum task offset value. And we describe how to create a dry scheduler that would be appropriate for doing this kind of thing in ERES2 Appendix 8. If we meet our requirements, that's fine. If we can't meet the requirements, we increase the offset for the task and try again. The maximum allowed offset is the task period minus 1 in ticks for each task. If we can't meet this requirement for a particular task, then we're not going to be able to schedule this task set. It's easy to take account of the scheduler overheads in this kind of modeling process. We simply reduce the maximum time available in the tick interval in much the same way that we do to set a maximum CPU load limit up here in this algorithm. So this is how we can create some simple code using a form of dry scheduler to determine the required parameters for a large set of tasks. This could be applied effectively to our Aero engine example. That brings us to the end of this video. please read Appendix 9 and Appendix 10 in the ERES2 book before you continue with the course. Thank you for watching.